Hello, my name is Mark Denker, and it is March of 2019. My experience as an analytical chemist is in a commercial laboratory performing X-ray photoelectron spectroscopy and secondary ion mass spectrometry. In today's talk, I'm going to give examples of surface analysis and failure analysis using XPS and Auger spectroscopy. The examples include film delamination by surface contamination, adhesive failure of sterile packaging, glass flakes and drug vials, bond pad analysis, and two examples of the analysis of electropolished stainless steel. No proprietary client data is used in this talk. Examples are taken from the EAG website or online searches. The first example I have here is of delamination of a metal layer. This is a copper laminate on a copper support, and some kind of contamination was suspected to be interfering with the adhesion or cohesion process at this interface. Potential suspects typically include silicones, fluorocarbons, or some other substance, and as little as a fraction of a monolayer contamination can cause failure. It is important to analyze a fresh failure location. The analyst should peel off copper foil just before analysis. That way, the suspected contaminant at the interface has minimum time to react with the atmosphere and change its bonding state. An XPS was used to look at both sides of the interface here. The table shows the concentration of the elements detected at the two surfaces before sputtering, obtained from high-resolution XPS. Both sides show phosphorus and high oxygen, along with nickel and molybdenum. Carbon is likely from air exposure. Depth profiles were performed with an argon beam to elucidate the layer structure. The copper is shown in black here. The nickel is shown in red. The oxygen is shown in green. The molybdenum is in blue, and the phosphorus is down here in purple. From the XPS profile data, a layer structure for the interface was constructed. This includes a phosphate contamination layer, under which there is an intentional 100 angstrom nickel molybdenum layer. The P level is, the phosphorus level is 2.5%, but since it was determined to be present as PO4, there will be 5 times this level of contamination atoms at the interface. The ability of XPS to provide bonding information and not just compositional data can help solve a problem such as this one. Silicones consist of an inorganic silicon-oxygen background chain, SiO, 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 shown here, with organic side groups attached to the silicon atoms. Here they're methyl groups. One of the commonly used silicones is PDMS, polydimethylsiloxane. Shown here is an XPS survey of PDMS, showing silicon, carbon, and oxygen peaks, along with a high-resolution spectra of the silicon 2p transition. The binding energy of the larger peak here is 101.8 eV, tentatively identifying it as a silicone Si, as opposed to metallic silicon, which appears down around 100 eV, or SiO2, which appears at 103.5 eV. However, silicates also appear around 102 eV, so if one needs to distinguish between silicones and silicates, a second surface technique such as TOF-SIMS would need to be done to confirm that. The next example is the adhesive failure of sterile packaging using both XPS and TOF-SIMS. A multi-layered aluminum sterile package for medical devices experienced adhesive failure at the interface between the polyethylene ethylene acrylic acid copolymer layer, which is heat sealed to this polyethylene layer. XPS data showed only small differences between the good and bad surfaces. The bad surface shows somewhat higher oxygen, you can see from the table here, which might be suggestive of additional compounds. More data is needed. The samples were then analyzed by TOF-SIMS which revealed the presence of the molecule, the organic molecule ergonox 1010 in the bad sample through the detection of the hydroxyhydrocinamate ions at 219, 233, and 259 AMU. Ergonox is a trade name for a series of organic molecules used as antioxidants for stabilizing polymers. It must have migrated to the heat-treated interface. The next example are glass flakes in pharmaceutical solutions, and the timeline for this is around 2010 to 2011. That's when a lot of work was done on this problem by a variety of labs. What is glass delamination? These are small, thin glass fragments, termed glass laminae, which are shed from the interior portion of glass containers and vials. Glass laminae are shed into and suspended in the liquid drug contained in the glass vial. Detection of the glass laminae can be very difficult during visual product inspections. The high-resolution SEM image here identifies regions on the interior vial surface which show indications of pitting and delamination. The factors contributing to glass delamination include the vial conditions after the drug is placed in them, including time exposed to the drug solution, temperature fluctuations during storage, and the chemistry of the solution, of the drug solution, and also the nature of the vial manufacturing process, the chemistry of the glass, and surface treatments that it's undergone. Glass delamination is an effect of glass corrosion. Glass corrosion can occur in silica glasses through three types of chemical reactions: acidic, basic, and neutral. And SEM analysis of these particles identify silicon-rich particles which are elementally and morphologically consistent with delamination. These SEM results identify the particles as coming from the glass and as not already present in the solution. EAG wanted to get a piece of the action for this problem, so we did our own series of studies. And the analysis of virgin vials shows the compositional variation caused by the manufacturing process. This was done by a series of XPS analyses along the interior wall, sidewall. And you can see here the boron oxide and the sodium oxide are depleted at the ends of the container and then enriched along the middle of the sidewall. This is speculated to be produced by heat gradients caused by how the vial is gripped at the two ends during manufacturing. The ends see a higher temperature than the middle does. This causes volatilization at the ends and redeposition in the middle during vial formation. We then performed a series of XPS depth profiles on vials exposed to low pH solution for 18 days and 64 days, shown here. This showed the creation of a layer depleted in boron and sodium and one enriched in silica. Increasing time of exposure led to a thicker depletion layer. For 18 days, it's around 50 nanometers, and then for the 64-day solution, it's around 75 nanometers. ICPS analysis, ICP mass spec analysis confirmed elevated levels of sodium and boron in the stored solutions. We also did a series of XPS depth profiles for a high pH solution. And at high pH, the mechanism of corrosion in the silica glasses is different than at low pH. Rather than removal of specific species, the SiO structure of the glass dissolves, shown here by the depressed counts here. This leads to the formation of a 75 nanometer aluminum oxide rich layer, significantly higher than in the bulk. From these data, it was concluded that the changes observed for both low and high pH conditions can lead to mechanical or chemical stresses that ultimately result in the production of microscopic flakes. These results have led manufacturers to use higher concentrations of aluminum and more stable divalent alkali atoms such as magnesium and calcium in the glass rather than sodium. The next example is bond pad analysis using Auger spectroscopy. Bond pads have been typically made of gold, but high cost is forcing transition to other materials such as aluminum and aluminum copper. Contamination and or the presence of relatively thick oxide layers on bond pad surfaces can lead to poor adhesion and electrical connectivity of the wire or ball attached to the bond pad. Auger's ability to do small areas is ideal for bond pads, which are as small as 100 microns. The initial Auger survey spectra of a good bond pad versus a bad bond pad shows a higher concentration of fluorine in the failed bond pad. Now mind you, neither is supposed to have fluorine on them, but in the good bond pad, I guess it's low enough where it doesn't affect the performance. Depth profiles were then performed on both the good bond pad and the contaminated bond pad, following the elements that were detected in the survey. These showed that both pads contained fluorine. However, the failed bond pad contained a higher level of fluorine, maximum about 15% as opposed to 10% here, along with a significantly thicker oxide layer. And this is probably the real issue, this thicker oxide layer. But the source of the fluorine was determined to be a foam material used to separate samples at the wafer level. The next example is XPS surface analysis of electropolished stainless steel. Electropolishing is the final treatment in the production of a corrosion-resistant stainless steel surface. It is an electrolytic process. It's the opposite of electroplating that entails the electrochemical removal of metal impurities, including carbon, silica, and free iron, from a stainless steel surface. This results in a surface rich in chromium and nickel oxide. Electropolished stainless steels are corrosion resistant because the chromium oxide serves as a passivation layer. It blocks oxygen diffusion into the underlying steel and thus prevents corrosion from spreading into the bulk of the metal. The chromium oxide layer is typically only 3 nanometers thick, which is 10 to 15 atomic layers. The XPS analysis of this is based on the Semispec test. The test, Semispec is the not-for-profit consortium based in Albany, New York, that performs research and development to advance chip manufacturing. And the test specifies certain certain instrumental conditions, including 35-degree takeoff angle to the detector, which enhances surface sensitivity compared to the normal angle that's used. The test protocol also outlines data analysis of the chromium ion spectra, including curve fitting. 3 peaks along with the binding energy positions are specified for chromium, 2 are specified to be oxide and 1 iron, and 5 peaks are specified for the iron, 3 oxide and 2 metal. Data are then used to generate chromium to iron ratios for both total and oxide. The total chromium to oxide ratio has to be greater than or equal to 2 for the metal to have passed, or for the surface to have passed. And then the oxide ratio for the 2 has to be greater than 3. SEM analysis is also performed on the electropolished surfaces. As we see here, boundaries between the grains results in a network of subsurface crevices before electropolishing. Contaminants that lodge in these crevices are protected from contact with cleaning agents, leading to subsequent migration of trapped contaminants onto the clean surface. The bottom one here, the deep grooves, cavities, and torn metal and other microscopic imperfections will also entrap and retain contaminants for this topography. SEM shows that the electropolishing smooths these features, and this reduces drag and minimizes contamination of fluids that come into contact with the EPSS surfaces. The last example I have here is an Auger analysis of corrosion on stainless steel. This Auger secondary electron image shows the surface of a piece of 300 series stainless steel, nickel and chromium stainless steel. The micrograph shows a series of extremely small features, most of which are only 25 nanometers in diameter. This SEM image was used to define points on which Auger was then performed. Points 1 and 2 are features suspected to be caused by localized corrosion, and point 3 is an uncorroded control area. The Auger elemental analysis shows a large amount of calcium along with a smaller amount of sodium level in the point 1 feature. Sodium's 3.5%, calcium's 38%. Point 2 shows sodium and not sodium, but sulfur and sodium contaminants. Note also that the chrome to iron ratios for these 2 points are different from the control area, 0.34 and 0.25 versus 0.7 for the control area. Auger mapping is used to show the distribution of selected elements on the surface. Shown here are 1 millimeter square Auger maps for calcium and iron. Although many particle defects were observed in the original SEM image, only a few of them appear to have significant calcium, as shown in the calcium map. Most of the smaller particles correspond to the increased concentrations of iron compared to the background of the control. This indicates that localized corrosion of the chromium has occurred within these 25 nanometer size defects, leaving the surface iron rich. A potential cause is speculated to be the presence of the sodium. Okay, this is the end of the presentation. Thank you for listening.